Testing. Testing.
Hi.
Hi. Good to see you. Long time no see.
Hey,
I guess
good to see you.
Yeah.
does that work?
So let me make an announcement before the next speaker. You guys recall we have a flat staff dessert outing tonight. So there'll be buses leaving from west side of. Actually, let me check on where, but is it Kittredge or is it by Force? Check that. I have a guess, but I need to check. But at 6 p.m. there'll be buses leaving. Take you to Prospect Mountain, and they'll leave pretty promptly. There'll be 2 or 3 buses. They'll be a little bit staggered, but please be there on time shortly before 6. And so we'll go up to Prospect Mountain. It's a really beautiful view. Have some dessert there. People can hike back if they want. Hike up if they want. It's by the empathy of Sunday and empathy. 1,000 feet up. So I hope you can all do that.
Okay. So it's a pleasure to introduce Michael Levin from the University of Chicago. So Michael is going to tell us about a couple of different topics. So first he's going to talk about exactly solvable string net type models in 2 dimensions. And then in the later part of his lecture, he's telling us about 3-dimensional topological order. So welcome. Okay, thanks. Thank you. So as Mike said, I'm going to start off the first lecture talking about some exactly solvable models for 2-dimensional topological phases. And then I'm going to move on to 3 dimensions and say something about our current state of knowledge about 3-dimensional topological phases. So to start off, as I said, the next couple lectures are going to all be about exactly solvable models for 2D topological phases. Okay, and now just to be clear, because you've heard so much about different types of topological phases, I'm sure, over the last few weeks, I just want to be totally clear about when I use the word topological phase, what I'm going to mean, at least for these lectures. So for my purposes, a topological phase is just something which has excitations. It has a gap, and it has excitations with non-trivial statistics, braiding statistics. So let me write that out. A topological phase is a quantum phase. So we're thinking about basically Hamiltonian with 2 properties, a gap, an energy gap in the bulk, and it has quasi-particle excitations with non-trivial braiding statistics. So for my purposes, I'm not going to be talking about symmetry or anything like that. It's just going to be, I'm going to be interested in phases where we have this interesting property that the excitations have non-trivial braiding statistics. It's a property that's independent of any symmetries. So in fact, the models that I'm going to be discussing basically don't have any symmetry, or whatever symmetry they have is totally irrelevant to all the physics I'm going to be discussing. Okay, so of course the classic example experimental realization of a topological phase are fractional quantum Hall states. But I guess you've probably also heard that there are hopes of finding topological phases in other systems, like, for example, in frustrated magnets, where these topological phases are sometimes called spin liquids. So those are kind of 2 standard examples. An example of something that is not a topological phase, according to this definition, is the topological insulator. Because, of course, that has an energy gap, but it doesn't have this non-trivial braiding statistics. And indeed, for those phases, symmetry plays an important role in their properties, unlike the ones I'm going to be talking about today. Okay, so this is the object I'm going to be discussing, and the goal of my next 2 lectures is going to be to construct some models for them. So the goal of the next 2 lectures is going to be to construct a very large class of exactly solvable models. And these are actually going to be, they're lattice models, and importantly, they're going to be models of spins. So we'll really be talking about topological phases that are built out of spins or bosonic degrees of freedom, which should be contrasted with, for example, fractional quantum Hall states, which at least are built out of electrons. So construct a large class of exactly solvable lattice spin models for topological phases. So that's what I'm going to do. And as I said, the important thing here is lattice and spin to contrast it with fractional quantum Hall, which is continuum and, of course, is built out of electrons. Now, you might ask, why do we care about these models? Why do we want exactly solvable models? So let me just give you a little bit of motivation. So I'll just list a few sort of types of applications that these models have. So one sort of very obvious application is that when you have an exactly solvable model, you can study it in complete detail. And that can be very helpful. You also have they're also extremely concrete objects to think about. So it's very helpful for sort of building intuition and playing around. I would say I didn't really understand topological phases until I saw some exactly solvable models for them and started playing with them. So that's one application. Another important application is that although these models are not going to be particularly realistic, so you may say they're irrelevant to, say, experimental realizations, the fact is that many of the properties that we care about topological phases are universal properties that are independent of the precise realization and that hold for the entire phase. And so for those universal properties, an exactly solvable model is just as good in terms of trying to understand them as any other model. And because these models can be solved exactly, you can derive these universal properties in a very concrete way. They can be used to derive universal properties of topological phases. And by universal, I really mean properties that hold for the whole phase. And so let me give you some examples. So 2 examples that I can think of interesting universal properties that were discovered from these types of models. One is sort of properties of boundaries. I'll talk about that probably next lecture or the one after. But you can use exactly solvable models to understand universal properties of boundaries of topological phases. For example, you can show explicitly that for some topological phases, the boundary can be gapped, because you can just explicitly construct a model for that boundary. And so that's kind of nice. Another universal property that you can get out of these models is the topological entanglement entropy, which I guess you guys have probably heard a little bit about. Have you? Yeah. So you can calculate the topological entanglement entropy explicitly in these models. And calculate it explicitly and also kind of get some intuition for where it's coming from. So those are 2 examples of universal properties that you can get out of these things. Another kind of application is basically to numerical approaches, in particular tensor network approaches to studying quantum many-body systems. So what's nice about these models, the ones I'm going to discuss, is that their ground states, we can write them, describe them as a tensor network. We have an efficient way to describe the ground state wave function, and then we can kind of perturb that ground state wave function, and that gives us trial wave functions to describe this phase. And in principle, you can use that for numerics to try to diagonalize or try to solve some Hamiltonian which isn't exactly solvable. You can use them as sort of trial wave functions. And then, of course, the fourth application, and this I'm going to put a question mark, is maybe these models can lead to some ideas for experimental realizations. But that's not clear, so I'm going to put a question mark there. They're very concrete, so that's nice, but as you'll see, the interactions are not physically realistic. Okay, so that's sort of I just told you these applications. We're going to discuss some of them in some of the later lectures, but it's mainly just to motivate why you should care, why you should pay attention to this construction. Okay, so as I said, I'm going to be talking about constructing a very large class of these models. But to get started, I'm going to start with a simple example, which I understand you've heard about a couple times. So I apologize, but I'm going to talk a little bit about the Tor code model. And the reason I'm going to do it is because the more general models that I'm going to discuss can be thought of as a generalization of the Tor code model. So it provides a really good sort of motivation for the more general construction. Okay, so now one thing that I will be doing with the Tor code model that maybe I don't know if the previous speakers did is I'm going to do it on a slightly different lattice. So you can have fun with that. It's a little bit different. I'm going to do the Tor code model on the honeycomb lattice, and this isn't that significant in any physical sense, but it's just going to be easier to generalize to the more general models that I'm going to talk about later. Okay, so let me remind you, this Tor code model is a spin 1/2 model where the spins live on the links of the honeycomb lattice. In this case, so each one of these guys is a spin 1/2. Okay, and just some notation, I'm going to label the links by L, and the plaquettes by P, and the vertices by V. Okay? And the Hamiltonian on the honeycomb lattice has the following form. It's a sum over all vertices and each vertex is a 3-spin interaction. It's a product of sigma L x, and it's sort of over these 3 spins. I'm going to draw it like this. Okay? So it would be like x, x, x. And then the second term, it's a sum over all plaquettes. And this is a 6-spin interaction, product of sigma Lz, and it's over the 6 spins around a plaquette. So I'll draw it like this. Okay? Z, 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 Z. Okay? And so that's the Hamiltonian. And I'm going to give some names to these 2 types of terms that appear in the Hamiltonian that'll be useful. So the first term, and again, maybe this notation is a little different from other approaches, so I'm going to just be clear about it. So this term here I'm going to call QV, this product of 3 sigma x's, and then this product of 6 sigma z's I'm going to call BP. And I use this notation because one kind of is related to a charge, and one is related to a flux. There's a mapping to lattice gauge theory, and they're related to charge and flux. That's the reason for the notation. Okay, so that's the model. Now let me just very quickly remind you why we can solve it exactly. So of course, the reason we can solve it exactly is every term in the Hamiltonian commutes with every other term. And that's going to be the case for all the models that I'm going to write down. So in particular here, QV commutes with QV prime. QV commutes with BP. And BP commutes with BP prime. Okay? And it's pretty easy to see why that's the case. The QVs commute with each other because they all involve sigma x's. The BPs commute with each other because they all involve sigma z's. The fact that these guys commute with one another, that's the only tricky part. But you can see the only time you have to worry about them not commuting is if they're close to one another. If they're far apart, they obviously commute. And if they're close, well, sort of the worst case scenario is your vertex is like right next to the plaquette. And then they overlap at these 2 spins. So the QV term involves 3 sigma x's. And then the BP term involves 6 sigma z's. And they do overlap, so you might worry that they're not going to commute. But of course, x and z anti-commutes. And since they overlap in 2 places, they will commute. OK, so since they all commute, that means we can simultaneously diagonalize them. And I'm going to denote, so we'll simultaneously diagonalize all the QV and BP operators. And I'm going to denote these simultaneous eigenstates by their eigenvalues in the usual notation. So BP, little bp and little qv. Okay? And of course, these eigenvalues are very simple. Well, the eigenvalues take two values, plus and minus 1. So BP and QV are they can both be plus or minus 1. And that's easy to see because if you look at these operators, they square to 1. If I take QV and I square it, so sigma x squared is 1. So obviously QV squared is 1. And similarly, BP squared is 1. So the eigenvalues are plus and minus 1. So each state is labeled by a whole infinite sequence of plus and minus 1s. Okay. Okay. So those are the eigenvalues. And of course, if I take one of these states, this state will obviously be an eigenstate of my Hamiltonian because it's an eigenstate of every term individually. And so the energy, so this is because BP squared equals QV squared equals 1. Okay. So each one of these states, as I said, is a simultaneous eigenstate of all the terms. So it's also an eigenstate of the Hamiltonian. And its energy is very simple. It's just a sum over all vertices of little qv minus the sum over all plaquettes bp. Okay. So we have the complete energy spectrum. These are the eigenstates, and these are their eigenvalues. And in particular, we can read off the ground state. The ground state, we want to minimize the energy, so we want all of these guys to be plus 1 rather than minus 1, because that's the lowest possible energy. So the ground state in this notation would be the state BP equals QV equals 1 for all plaquettes and all vertices. Okay? What about the coupling constants?
You don't have any coupling.
Yeah, I took them out because I think they're not there in the original paper by Kataev either. I didn't. The reason is that, it doesn't really do much. Just you would just have some coupling constants here. It wouldn't change anything really about the. We're really interested in the ground state, so it doesn't really change the ground state. Yeah.
So we have seen particle realized in a square lattice.
Yeah.
Hexagonal lattice.
Yeah.
I believe also seen on Kagome lattices. Are there other examples on other realized?
You could do it on. Yeah, you can do it on any basically planar lattice, and it has the same properties. Yeah, same properties. It's just the only reason that I'm doing on the honeycomb lattice is because the more general models that I'm going to discuss are easiest to write down on the honeycomb lattice. Again, those models can also be written on other lattices in principle, but unlike the Tor code, which kind of takes an equally simple form on all lattices, those models are simplest on the honeycomb. So I kind of wanted to start off on the honeycomb to prepare you.
Probably you're needing is that the QV and BP share two operators.
Yeah, but that's true for any. You can see that's going to be true for any lattice, basically.
Okay.
Mm-hmm.
I guess the reason I asked about coupling is that you can imagine tuning it to have a transition, but is there anything interesting about changing, when you bias K1 versus K versus K prime, or have them go negative?
So yeah, you could consider the phase where you could put plus signs here, for example. It has similar properties if you don't care about symmetry. So if you include translational symmetry into your description, there's some differences. But without translational symmetry, it has the same properties basically. Yeah. Yeah.
I know it's like a standard way to derive the ground state. Just say all operators commute and just put everybody to plus. But is there any way to understand, since BP is composed of 3 operators or 6 operators?
6.
Yeah, so naively, if I take a look at this operator, there are multiple ways to make this product to be plus.
Yeah.
How do I understand then the ground states don't have a macroscopic number?
Okay, very good question. So I didn't compute the degeneracy. This argument here just tells you, actually all I really showed you is that if there exists a state with its properties, it has the lowest possible energies. I didn't prove you the state exists, and I didn't prove it's unique. And in fact, whether it's unique or not depends on the geometry in which the model is defined. And so for a proof of that, actually, I'm going to show you a way to prove that in another context a little later. So just take it on faith right now, because I don't want to spend time on it. But I will give you a way to prove in even a more complicated context to calculate the degeneracy of the ground state space. There's a simple trick for doing it, which I'll tell you about. And it lets you prove that, for example, if you do this in on a sphere, so if you imagine drawing this lattice on a sphere, now of course you can't really do a honeycomb lattice on a sphere, so you have to have some defect in it. You could still write it down, and you can prove that the ground state is unique on a sphere. And if you did it on a torus, the same calculation would give you a 4-fold degeneracy. So I'll show you a way to do that. But for now, just think of this as defined on an infinite plane or on a sphere, and then just take on faith that it's unique. There are other questions? OK. So that's the ground state. Now, of course, we're also interested in the excitations. And there are two types of excitations in this system. So basically, you can either have one of the QVs equals -1. That's going to cost some energy instead of +1. Or you could have one of the BPs equals -1. OK? So if QV equals -1, that's one type of for some V. So that's some kind of defect. And that's what we're going to call a charge excitation. And then I said, again, the other kind of defect is you can have BP equals -1 for some plaquette. And this we'll call a flux excitation. And just to draw it out, because I'm going to probably need this. So let me just show you, of course, where do these excitations sort of live? Well, that's kind of a bad lattice. So the charge excitation lives on some vertex, let's say this one. It's associated with a vertex. It's like a defect living on the vertex. And the flux excitation lives on a plaquette, say P, here in the center. OK. Now, both of these excitations cost energy, and you can just see from this, they actually both cost energy 2. Right? Because if I flip QV from +1 to -1, it's going to cost energy 2, and similarly here. OK. So the excitations cost a finite amount of energy, and so then if you believe that the ground state is unique, which I didn't prove for you, then this means we have a nice gapped system. So we've achieved at least this first part of this definition here. So as I said, we have a model which is gapped. So that's nice. Now, what I wanted to do second is I wanted to show you just very quickly, although I've heard you may have seen it before, just very quickly, I want to prove to you that this model has the second property. It has quasi-particles with non-trivial braiding statistics. And the reason I'm going to do this is because, well, it's a very important calculation, and it kind of motivates why we care about why exactly solvable models are so nice, because we can really calculate their statistics very explicitly. So in particular, the non-trivial braiding statistics in this case is if I take a charge around a flux. So here's my flux sitting somewhere here. Here's my charge sitting here. And if I move it around, it'll pick up a statistical vary phase. And that statistical vary phase is -1. OK. So I just want to convince you of that fact very quickly. OK, so the key idea is that, instead of, so you probably heard the definition of statistical Berry phase is that you trap two particles in some potential wells, and you adiabatically move one potential well around another, and you calculate some Berry phase, and then, from that you can, there's some statistical component of that Berry phase, which is this -1. So it turns out that you could do that. You could really write down some potential well on the lattice and then slowly change some parameters, and continuously change some parameters so that the center of this potential well moves. But it turns out that because this thing is a topological phase, it kind of doesn't matter. The details of what potential well you use or how you move it don't really matter. So what we're going to do, instead of really using a potential well to move it around, we're just going to move it using some local operators, which you can imagine as being affected by actually physically moving some potential well. So we need to do this, we need to take this charge and just physically move it with some operators around the flux. And it really doesn't matter what operators you use. As long as you manage to get the particle all the way around, you'll get the same answer. So we'll do the simplest way of moving the charge. So the simplest way of moving the charge is to apply the sigma z operator. So I claim for you that sigma z allows you to move a charge. To see that, let me just draw a small part of the lattice. Let's suppose you have a charge that's this. Sorry, let me draw. This is the spins. And suppose you apply sigma z on this link right here. So my claim is that if you had a charge sitting here, after applying sigma z, it will move over here. And that's easy to see because if you look at the definitions, if you apply sigma z, so if I have a charge here, that means qv is equal to, I guess, minus 1, right? And let's say qv equals +1 over here, right? If I apply sigma z, it anti-commutes with both of the two qv's, right? Because z anti-commutes with x. And so it's going to flip. If I started off with -1 +1, it changes it to +1 -1, which means the charge moved from here to here. So sigma z allows us to move a charge. And so then to move a charge all the way around here, we just have to apply a whole bunch of sigma z's. So basically what we're going to do, go back over to this picture. We're going to take this charge around here by just applying a whole sequence of sigma z's on some curve like this. It goes all the way around. And this curve I'm going to call C. This is the curve on which the charge moves. So I'll call this curve C. And so what we need to do is just see what happens if we move the charge all the way around. So we want to take product of sigma z along this curve, and we're going to apply it to some initial state, which I'm going to call P0 V0. So this just means I have a plaquette excitation at plaquette P0, a flux excitation at plaquette P0, and a vertex excitation at V0. So actually, I should really label this to be clear. This should be P0, and this should be V0. Okay, so this is my initial state, and then I'm going to move it around and see what happens. So if I do this, what do I get? Well, you can use a simple identity, which is basically Stokes' theorem, that says if I take the product of sigma z along some curve like this, it's the same thing as taking the product of the BP operators inside the curve. Because if I multiply all the BP operators together, all the z's cancel in the interior, and I just get this thing in the exterior. So basically, it's an operator identity. I can replace this by product of BP for P in the interior of the curve, acting on P0 V0, right? That's just an operator identity. And then what about when I act this on this? Well, this has every one of these BPs. If I act on this, it gives me +1, except for one of them, which is the BP0, which it's an eigenvalue of that with eigenvalue. It's an eigenvector of that with eigenvalue -1. So this has all bunch of +1s and one -1. So I end up with minus P0 V0. Okay. So we got this minus sign. Now, of course, actually, I want to be clear. This in itself does not prove they have non-trivial statistics. This doesn't really prove anything. You might be tempted to think you're done, but you're not quite done. And the reason is that, in general, when you move something, a charge around a flux or two particles around each other, there's the Berry phase has two components. There's a topological Berry phase, but there could also be some other kinds of Berry phase, statistical Berry phase, and so on. I mean, geometric Berry phase, for example. Maybe there's a magnetic field or something. It picks up some other phase. So to really calculate the statistical Berry phase, you have to compare two different processes to extract the purely topological component. So what we're going to do is compare a process where we move a charge around a flux with another process where the flux is not in the center, but we move it around exactly the same curve. So you need to compare the two, and then the difference between the two tells you the topological Berry phase. So without the flux in the center, if you go ahead and do the same calculation, so to be clear, I'm going to put the flux somewhere. Instead of being in the center, I'm going to put it on some other plaquette, say down here, P naught prime. So if you do the same calculation for that initial state, so you take product of sigma ZL, and you apply it to P naught prime V naught, so where the flux is no longer in the center, and you follow through the same calculation, you can use the same identity. I'm running out of chalk here. Do you have other? Okay.
There's also big
Some of these are yellow, or? Okay. So you do the same calculation now. Now none of the plaquettes in the center have, they all have eigenvalue +1 because this flux is over there. And so if I do the same calculation, I'm going to get a +1. So this becomes plus P naught prime V naught. So the crucial point is that I have a different phase in these two cases, and that difference is exactly -1. That tells you that the statistical Berry phase, that way we've extracted the purely topological Berry phase from the geometric or other types of Berry phases that could be there. That is -1. So it's this comparison that really proves that we have non-trivial statistics. I just wanted to make that point because I think sometimes people forget that you really have to make a comparison between two processes to extract statistics. So far, so good? Okay. Okay. So if there aren't any other questions, I'm going to now sort of move towards these more general models. So to do that, I first want to sort of look at the Tor code in a slightly different point of view. And that will motivate the more general models, which I'm going to discuss. OK. So this other point of view, I guess I'll call it the string picture. It's a sort of slightly more geometric way of visualizing the Tor code. OK. And it's very simple. Basic idea is that whenever we see, we're going to think about things in the sigma x basis. Turns out that's like slightly clearer in this, at least on the way I've written the Hamiltonian. And we're going to translate whenever we see a link where sigma x is equal to -1, we're going to say that there's a string on that link. String on link L. OK? It's just another language for spin. And similarly, if sigma Lx is equal to +1, we'll say that there's no string on that link. OK? And so this just gives you a dictionary for translating some arbitrary spin state, at least in the sigma x basis, some configuration of sigma x's, into a string state, where the strings are now living on the links of the honeycomb lattice. OK? All right, so now that's all fine. That's just basically changing words from spin to string. But then there's some nice sort of geometric interpretation of these different terms. In the Hamiltonian. OK, so let's think about the QV term, which I've unfortunately erased. So if you remember, that QV term was just a product of 3 sigma x's. OK, so that term favors configurations where the product of 3 sigma x's is equal to +1. Right, where QV is equal to +1. But if you think about it in this language, that means that at every vertex, I must have an even number of strings incident on that vertex, because sigma x equals -1. There have to be an even number of sigma x equals -1s for the product to be +1. That means an even number of strings on this vertex. That means either 2 or 0. Well, what that means is that the strings don't end. They always form closed loops. So this basically favors configurations. Another way of saying it is it's favoring configurations where the strings form closed loops. So as an example of such a configuration, so a typical configuration that would be, say, favored by this term, by just the QV term, would be something like this, for example. So where I have strings on that loop and let's say a string on this loop. And you can see at every vertex, there are an even number of strings incident in that vertex, so product of sigma x is equal to +1. OK, so the QV term just wants you to have closed strings. What about the BP term? Well, the BP term also has a simple interpretation. So the BP term you can think of as a string hopping term. So while the QV term just wants you to have closed loops, the BP term is going to make strings, gives an amplitude for them to fluctuate. So let's just see how that works. So let's imagine we start off with some state with the strings that look like this. This is supposed to be some part of the honeycomb lattice. OK? So that means sigma x is equal to -1 on these links and +1 everywhere else. Okay. Then if you apply BP, if you apply the BP operator here, what does it do? Well, remember, it's a product of 6 sigma z's. So what it does is it flips the string occupation on every link. So it will change you to something like this. Right? Because it's flipping these two. These two will be unoccupied, and then these 4 will be occupied. So it's making the string move. In addition, if you apply it to something where there's nothing at all, there's no strings at all, it will just create a little loop. So if this is supposed to be the action of BP. So if I take something like this where there's nothing at all and I apply BP, well, again, it flips the occupation on all 6 of these links. So it's going to give me something like this. Of course, conversely, if I apply it to something like this, it would take me back to there. So it kind of creates or destroys strings, and it moves them around like this. Okay, so that's why we call it a string hopping term. Okay. Okay. Are any questions? Okay. So now we can visualize our 2 terms in our Hamiltonian as one term favoring closed loops, the other's making the strings fluctuate. What about the ground state? The ground state also has a nice geometric interpretation in this language. So I'm going to label the ground state by capital phi. And you could kind of guess, well, the ground state's going to consist only of closed loops because it's an eigenstate of QV with eigenvalue +1. And it's also going to have to consist of many, many different kinds of loop configurations because it's an eigenstate of BP, and BP is making them fluctuate. So in fact, it turns out it's an equal-late superposition of all possible closed loop configurations. You can easily convince yourself that this is an eigenstate of both those terms with eigenvalue +1. And this is the ground state. In fact, this is the unique ground state if you do it on an infinite plane or on a sphere. OK, so that's the ground state. And equivalently, if you want to write the ground state wave function in sort of typical notation, you would write it as phi of x is equal to 1. The amplitude for any configuration is 1 as long as for all closed string configurations. So it's a very simple wave function. Okay. Okay. So if you just want to sort of picture it, if you kind of forget the lattice and you think in the continuum, which is something that I'm going to do kind of shortly, then you could say it's a superposition of configurations like this, just some crazy, any configuration of closed loops. But it's a superposition, this plus some of arbitrary configurations like this. And so you can think of this as a little bit like a condensate, because if you think of a usual Bose condensate, it's a superposition of particle occupation numbers where the particles are located everywhere. This is a superposition of strings with their positions located everywhere. So we can call it maybe a string condensate. It's just some language, but explain some words. A little bit like a particle condensate, but made as extended objects. Okay. So it's a string condensate, and actually it's a kind of very interesting string condensate. It's kind of the most, just like with a particle condensate, you can imagine kind of tuning some parameter that takes you from a condensed phase to, let's say, an insulating phase. You can imagine an ideal condensate, which is kind of like a uniform superposition of all possible occupation numbers. This is also a kind of ideal condensate because it's a superposition of all of them. There's with equal weight. So we can call it an ideal condensate. Phi is sort of an ideal condensate. And if you want to be more precise about in what sense is it really ideal, well, what's special about it is it has zero correlation length. So if you look at spin-spin correlators in the state, you can convince yourself as long as the two spins are basically, maybe they have to be two lattice constants apart or something. They have to be one or two, they can't be right next to each other. But as long as they're not exactly right next to each other, actually, if it's just a two-spin correlation, even if they're right next to each other, it vanishes. But even for more complicated spin correlations, as long as they're just a few lattice sites apart, the correlation function is exactly zero. So in other words, the decay length in this case is just, it's zero. It goes to zero immediately. So it's an ideal condensate in the sense that its correlation length for some kind of spin-spin correlation is zero. And that's related to the fact that the Hamiltonian is the sum of commuting projectors. Okay, so it's kind of like you can imagine a maximally disordered state. If you have an Ising model, you have maximally ordered and maximally disordered. Those two extremes, the correlation length vanishes. And this you can think of as kind of an extreme string condensate. And because the correlation length is exactly zero, if you imagine doing some kind of RG transformation, it's kind of self-similar. It has no length scale. So I'll use this terminology. We can think of it as almost like a fixed point. A zero correlation length fixed point. Again, it's just some terminology or some intuition. It won't play a role in any of the results. It's just in kind of motivating the picture. Yeah.
You say it has to do with the telecommuting terms. Is that always true? Can you say that in general?
Yeah, let's see. If you take an arbitrary Hamiltonian that's a sum of commuting projectors, and let's say has a unique ground state, I would think that's true, yes. I think if you go, there's some length scale for the size of your commuting projectors, but if you go beyond that distance, I think you would expect to be zero. No, well, but if you look at BP, right, it acted on six of them, right? So I'm saying imagine I had a more complicated Hamiltonian that acts on like 50 spins in some little disk. Obviously, the correlation length, when I say zero, what I mean is if I take a spin here and then a spin that's probably has to be further apart than the size of this block, then the spin-spin correlation will vanish. The connected correlation will vanish.
Vectors have all added values 0 and 1. What do you mean by these terms being projected?
Oh, Sorry. Just add 1 to them. So this one had, or add 1 to it and divide by 2. Sorry. Yeah, I with the toric code, I tend to not add in those extra 1s, but you can if you want to make them projectors. Yeah. Yeah. So what I was just saying here is that spin-spin correlations vanish if the spins are distant, even 3 lattice sites apart. And yes, and I think that is a general property of commuting projector Hamiltonians, although it might not be 3 lattice sites, it might be 50 if your projector acts on 50 spins or something. Other questions? Okay, so this is all motivation. So what we have shown is in this very simple model, we've got a model for a topological phase, and the wave function is kind of a condensate of strings, and it has correlation length 0. You can think of it as sort of an ideal condensate. Okay, so if you like, that's just going to be motivation for what I'm going to talk about now, which is how we can construct more general models that realize other types of topological phases. So now I want to talk about generalizing the toric code. Okay, so first just some language. So this generalization is going to involve not just strings, but strings that branch. So the term that I'll use is string net. So let me tell you what is a string net or string nets. So basically, these are going to be networks of strings with branching. Okay, and now actually, not only will they have branching, but I'm also going to allow the strings to have different species. Okay, so there are going to be different types of strings. Strings can come in different types. And as I said, they can branch. They can branch. And actually, for simplicity, I'm only going to allow for 3-fold branching. It turns out that's enough to get every phase. And that's also why we're using the honeycomb lattice, but we'll come back to that. So 3-fold branching only. Okay, so it's basically some strings. So let me draw a picture of an example. So like a typical example of a string, well, this is actually a configuration. A string net configuration would be something like this. I'm just, it's going to be some whole collection of these guys in space, located in different places in space. And I said they can come in different types. So, like maybe this is type 2, this is type 1, this is 2, 2, and 2. And this is 2, 2, 2, 2, 1, 1. Okay. So that would be a example of a string net configuration. And it should maybe be clear from this definition that really what I'm talking about, if you like, is in mathematical language, is just a graph. Mathematicians would call this, each one of these guys, it's a trivalent graph. So these are labeled trivalent graphs, which I guess don't have to be connected. Can have many components. Okay.
So what's the difference between 1 and 2?
You think of it as like if you have 2 species of particles, like spin up and spin down. So I'll explain in a second, but having a type 1 string here and having a type 2 string, those would be different states in your Hilbert space. So the Hilbert space is going to consist of all these different, the basis for the Hilbert space is going to consist of all these different configurations in space. You can think of them as living on the honeycomb lattice. So you take some configuration of these guys living on the honeycomb lattice, and every different configuration will be a different orthonormal basis element. Yeah?
Can I think of these as like a lattice of 3-level systems, and you can decide?
Yep. Yeah, in terms of a spin model, this would be a spin model where each spin I'll explain that later, but each spin can be in 3 states, 0, 1, or 2. 0 we won't even draw. 1, we draw a type 1 string, and 2, we draw a type 2 string. So just like before, for the Tor code, we translated spin states into string states. You could do that for a 3-level system as well. And when it's 0, you would say there's no string there. When it's 1, you would draw a type 1 string. And when it's 2, you draw a type 2 string. And then the states would correspond to pictures like this. Yeah? That's the next thing I'm going to talk about, right? So like, there's some structure, right? So I need to explain that. Other questions? Yeah? Yeah, this is all 2-dimensional models. So you should think of these things as living on the honeycomb lattice. But I'm not going to draw the lattice for a while. Yeah?
How we never considered threefold branching in all our discussions over the expectations, or you're going to go with
Oh, so that's why we're generalizing the Tor code. So the Tor code could be a special case which doesn't have any branching. So what I'm saying is I'm allowing threefold branching. So I'm going to consider a whole class of models, which in principle, some of which have threefold branching, some of them have no threefold branching, but they can have threefold branching. So I was just trying to show you a typical example that includes branching. But the Tor code will be a special case. Other questions? OK. So that's what a string net is. And then just a string net model, which is the kind of model which we'll eventually talk about. It's a quantum mechanical model that describes the dynamics of these string nets. Just like the Tor code, you could think of as a quantum mechanical model that describes the dynamics of strings. So this is a quantum mechanical model. And eventually, we'll write it as a lattice spin model that describes the dynamics of string nets, of these more general branching type objects. OK? OK. I guess I should put an S here. OK. So now, as was pointed out, there's some structure to these string nets, right? Like, I have to explain. What kind of types of strings am I going to have? Like for each model, I'll have some number of string types and some type of branching. There'll be some structure. So to specify a string net model, I have to give you some data. Specify a string net model, you need to provide data. At least some very basic data to tell you what types of string nets you're going to be talking about. And I should say, I'm going to tell you that data in a second. But I should tell you, as a disclaimer, I'm not going to be telling you the most general string net models. I'm going to be telling you a kind of special case, which is easier to present. I'll talk a little bit about the most general case very briefly later. So I'm going to be focusing on a special case, a special class of string net models. So just keep in mind that I'm not telling you the most general case. That's all I'm saying. We'll come back to what's the most general case. OK, so what's the data to specify a string net model? Well, at the crudest level, I have to tell you what are the types of string nets, that make up this, that I'm describing the dynamics of. How many string types do I have, and so on. So, data. So there's two pieces of data I have to specify. So one is, I've already alluded to, it's the number of string types. Which I'll call n. And by convention, I'm going to label my different strings as 1 through n. So I'll draw them like this, where I goes from 1 to n. OK? So that's the number of string types. The other thing I have to tell you, of course, is about the branching. So there's something called branching rules. And these are rules that just tell you what types of branchings are allowed. OK? So if you like, the branching rules is just a set of triplets of strings that are allowed to meet at a point. So triplets I, j, k allowed to meet at a point. Okay, so that's like, which types of vertices are going to be allowed. Okay. So let me give you an example. So an example of the kind of data that I could tell you is I could tell you that I have 2 string types. So the number of string types would be 2. Number of string types n equals 2. And I could tell you that the following triplets are allowed, the following branching rules. So I would say that 1, 2, 2 is an allowed branching. Type 1, type 2, and type 2 string can meet at a point. And also 2, 2, 2. 3 type 2 strings can meet at a point. Okay? So I could tell you this data. And no, 1 is, I'm going to actually use 0 to denote trivial string. I haven't even told you what, 1 is a non-trivial string. All the string types at the moment are non-trivial strings. So this would be an example of some data, and an example of a typical configuration in the Hilbert space or whatever for such a model would be something like this. Right? You can see this only has 2, 2, 2 branchings and 1, 2, 2 branchings. Right? Yeah. So for the moment, these are. I'm going to tell you what the Hilbert space is for my model. Actually, that was the next thing I'm going to say is once you specify this data that I've told you here, then you can then this tells you what the Hilbert space is for your string net model. The Hilbert space is just going to be the set of all possible string net configurations. Think of them maybe as being on the honeycomb lattice that obey this restriction. So let me write that down. So this data specifies the Hilbert space. I haven't yet talked about the Hamiltonian. So you can think of it the string net Hilbert space. The orthonormal basis for that Hilbert space is the set of all string net configurations on the honeycomb lattice that obey the branching rules. So this is a set of all string net configurations on the honeycomb lattice, though I never am going to draw the honeycomb lattice, that obey the branching rules, obeying the branching rules. Okay. So far I've just told you, if you like, the Hilbert space of the models that we're going to talk about. Well, it's not even quite the Hilbert space. It's, if you like, it's going to be kind of the low energy Hilbert space. If you think about the Tor code model, for example, the full Hilbert space included configurations where strings ended, right? But at low energies, let's say we're below the energy gap of the QV operator, the configurations always involve closed loops. So strictly speaking, this is going to be, if you like, eventually I'm going to write down some spin model, and the low energy Hilbert space below the QV terms energy scale is going to consist of these kinds of configurations drawn on the honeycomb lattice. So in particular, the ground state is going to be some superposition of these configurations. Yeah.
I didn't understand from your rules if you only allow closed graphs.
I what?
If you only allow closed graphs as opposed here?
Yeah. What about it?
You only allow
Oh,
this, or do you allow
that's right. So yeah, that's right. So I don't have, I don't allow a string to end. That's right.
You don't have those like zero.
Well, I leave those out. So yeah, that's right. I haven't even mentioned the type 0 string, but if you include that in your notation, then that's the way you would say it formally is I wouldn't allow 002 is not allowed. But in my notation so far, I haven't even told you, I haven't even mentioned type 0 string. I'll bring that up in a second, but it's sort of not necessary at this level. Yeah. Oh, so each, yeah, maybe I'm being unclear. Each configuration is a distinct orthonormal state. So like, so if I draw on the honeycomb lattice, I'm just trying to clarify that geometry matters here. It's not just topology. So like, if I have a type 2 string that lives on this link, let's say, and type 0 string everywhere else, that would be one basis element. Okay? And then another basis element might have a type 2 string that, looks like this. That would be another basis element. But then most basis elements contain more than one string. They have like, thousands of strings all over. That's each one of those configurations is a distinct orthonormal basis element. The Hilbert space, a general state in the Hilbert space is a linear superposition of all possible coefficients in front of each of these possible states. Yeah. No. At least the models I'm going to write down, some types of branching rules we don't have a model for. So there are some restrictions on which types of branching rules we can find models for. Yeah. Yeah. You mean like you can break up the strings into two? Oh, I see. Yeah, I have to think about that. It might mean that you can somehow factor your system into two pieces. Yeah. Are there other questions? Okay, so if this doesn't, it's going to get more concrete as we go. So, so don't worry. We'll write down a real model, and then maybe you'll be able to see exactly what all these words mean. But I'm just trying to kind of set the stage, because the thing is, I'm not going to, that's the next thing I'm going to tell you about. I'm not going to just write down the Hamiltonian and then the way I did with the Tor code. I'm actually going to first write down the ground state wave function. And after I have the ground state wave function, then I'm going to tell you how to write down the Hamiltonian, which has it as its ground state. So because I'm kind of working backwards like this, that's part of the reason why I'm sort of telling you all this language before I write down the very explicit model. Okay, so as I said, our strategy is going to be start with the ground state. So the strategy for building a string-net model, and yeah, so actually I should just clarify something. So what I've told you so far is a Hilbert space, right? To write down a model, I have to give you a Hilbert space and a Hamiltonian. But the way we're going to do it is I'm going to first construct a ground state wave function. It's going to be some superposition of these string net configurations. And then I'm going to tell you how to write down a Hamiltonian, which has it as ground state. And the Hamiltonian that I write down is going to be a real honest-to-goodness spin model. You don't have to know anything about strings to understand the Hamiltonian. It's just that if you have this understanding of strings, the Hamiltonian makes more sense. So I'm first going to construct a ground state wave function, and then I'm going to construct the corresponding Hamiltonian. Okay. So as I said, my ground state wave function is going to be some wave function that is going to be some superposition of all these different string net states. Okay. People have discussed them. I'm not going to be talking about them. So everything is going to be, you can think of it as coming out of a spin model, ultimately. OK. So following this plan, the next thing I want to do is construct wave functions that are wave functions that belong to, whose describe different topological phases. So these are going to be string net wave functions. Maybe I should say that explicitly. Constructing string net wave functions. These are ground state wave functions. OK. So we kind of want to generalize that simple Tor code wave function, which was just 1, right? We want to generalize it to these cases where we have branching. So we want to write down some wave function. And actually, the wave function, I not only want to have it be a wave function, I want it to be kind of a fixed point wave function, to have this sort of 0 correlation length. Because only those wave functions do I have any hope of finding some commuting Hamiltonian that has commuting projector Hamiltonian that has it as its ground state. So I'm going to be looking for fixed point wave functions. And that's a little vague, but hopefully it gives you some intuition. They should be wave functions that kind of have no length scale. And then I'm going to hope I can find some Hamiltonian which has it as its ground state. So to write down a wave function, I need to tell you for each configuration of string nets in space, what is the amplitude? So for some configuration like this, I have to tell you some number, right? Some complex number. Just like in the Tor code case, that number was just 1. OK? So yeah, this belongs to the Hilbert space. So so I wrote this in wave function form. If you wanted to write it in sort of ket form, it would be like a sum over different states that look like that, with some numbers out front. And that belongs to that Hilbert space that I told you about. There should be branching here. OK, so we want to write down this wave function. Now, the problem is it's not so easy to write down any wave function, really. How can we write it down? And the problem is that, well, there are lots of different configurations of strings in space. There are a lot of different numbers we have to specify, right? It's a very complicated object. So how can you hope to write it down? And then what makes matters worse is, only very special wave functions are going to be a ground state of any Hamiltonian, much less a commuting projector Hamiltonian. OK, so we can't just guess arbitrarily wave functions. We have to have some strategy. So the strategy is going to be, instead of writing down a wave function explicitly, just telling you a formula, I'm going to describe a wave function in terms of some constraints that it obeys, some local constraints. And the reason that's a good thing to do is, first of all, it lets you write down a really complicated wave function that you can't even write down in closed form. And second of all, because you're writing it down in terms of local constraints, it's naturally something that could be the ground state of a local Hamiltonian. It's a very sort of physical construction. Ground states of local Hamiltonians kind of obey local constraints. So the idea is going to be to define the wave function implicitly, not explicitly. And we're going to do it using local constraint equations, which are going to uniquely specify the ground state. OK. OK. So let me tell you what those constraint equations are. Now here there's definitely, let's see, maybe I'll leave that up. Well, no, I think I don't need it. OK. So what are the constraint equations that this wave function is going to that are going to define our wave function. So they're actually going to be four different constraint equations. Okay, so the first equation, I'm going to write it symbolically like this. It says that if I take the amplitude of some configuration, drawn on the honeycomb lattice, some way, the amplitude will be the same if topologically equivalent configurations have the same amplitude. Okay, so the amplitude for another configuration looks like this. I don't know, stretch it a little bit. I don't know. They'll be the same. Okay, so this is going to be my, if you like, this is an ansatz. I'm going to only consider wave functions that obey this property, that they're kind of, if you like, topologically invariant. Different states that are topologically equivalent have the same amplitude.
Can I just ask a clarifying question? So on the right side, you wrote a general state is a linear combination of the string configurations with coefficients.
Yes.
These coefficients are independent.
That's right. And that's what we're trying to compute. The ground state will have particular numbers there, and we're trying to compute those numbers. And I'm going to specify those numbers for you, but I'm not going to specify them explicitly. I'm not going to give you a formula for them. I'm going to give you an implicit formula for it, which will become clear in a moment, which will define the numbers. You can compute them, but it's not like a closed form formula. And then once I give you that formula for the that implicit description of the wave function, then I'm going to write down a Hamiltonian, which has it as ground state. Okay. So my first part, if you like, of the first equation is that phi is topologically invariant. Okay. The second one, and okay, by the way, why motivate that? Well, remember, we want something that's fixed point, so it certainly shouldn't have any length scales in it. So the simplest thing, it's just some motivation. You might think this would be a natural thing. We don't want it to have any length scales. Maybe it should be topologically invariant. Certainly, that's an example of a state which has no length scales. So it's a reasonable candidate for a fixed point wave function. Okay. So the second equation. The second equation is that if I have some configuration of strings in space, and somewhere in that configuration I have a loop, a type I loop, then I'm going to say the amplitude for that configuration is the same thing as the amplitude for the configuration without the loop. I'm just going to draw a dot here, up to a factor di. So maybe I'll write down these equations and then I'll explain them. So because there are four of them. So that's one of them. The next one looks like this. And I'll explain what these mean in a second. I think it's better for me to just write them down first. Okay, and then the last one, 4, is this. IJKLM. ILJKN. Okay. And one more thing I should tell you before I explain all these rules. Di and f are going to be some numbers, complex numbers that are going to specify our wave function. They're complex constants. This is a complex constants. This is a complex tensor, if you like, that specify the wave function. That define my wave function. Okay, so So I should explain to you what these rules mean. Okay. Okay, so the first rule I already explained to you. I'm going to assume my wave function, the amplitude is topologically invariant. Any configuration that's equivalent to any other configuration, the two have to have the same amplitude. Okay, the second rule is a little bit different. What this says is that if I have some arbitrary configuration with a single loop in it, type I loop, the amplitude for that is equal to the amplitude for the configuration without the type I loop multiplied by some number di. So if you like, a type I loop is worth di. You can remove it, but you have to multiply by di. So this is, if you like, this equation summarizes an infinite set of equations. You know, I can have arbitrary garbage out here, and it says the amplitude for that is the same as di times, you know, the same stuff over here, right? So it says you can delete a type I loop at the cost of multiplying by di. Again, you could vaguely motivate this from this fixed point of view, because type I loop, you can imagine kind of, as you go to longer and longer distances, it kind of shrinks to a point. It should be, you might imagine that there's some proportionality relation like this. Anyway, that's just some vague motivation. No. Yeah.
It's a little strange in light of the rule 1, because rule 1 allows you to add loops.
No, rule 1 just allows you to stretch things.
Right, but you can think of stretching things as like adding a loop on top of the left picture. So let's say you have a straight line across the bubble,
Uh-huh.
and you add a loop to it. You know, you kind of,
Oh, you're imagining multiplying. I think I almost call that multiplying. You're imagining applying an operator like this,
like
which
that.
makes it
And
move.
then that
Yeah.
makes it into that.
Yeah.
So, but that multiplication is an identity on that wave function. On the other hand, rule 2 says it's a guy.
Right. Yeah, so both are going to be true, actually. So let's see. Maybe it'll be when I write down the Hamiltonian, I can address that. For the moment, I'm not talking about operators. But the true ground state will have the property that if you multiply by a little loop, it gives you a factor of di, actually. Yeah. That's right. Yeah, so this says, so number 3, so let's get to number 3. Number 3 says if anywhere in my picture I see something like this, where a type I string comes into a bubble with some arbitrary labels and a type J string leaves, the amplitude is 0. Okay?
Even if INK and JLK are allowed branch groups?
Yeah, yeah. In fact, that's the case. I should say I'm always assuming whenever I draw these pictures that they're the allowed branchings. Yeah. Now, why is this reasonable? Again, from some vague fixed point of view, from far away, this looks like a type I string coming into a type J string. But I should have said this, but we don't allow that. Right? Someone asked whether type I strings could end. That we don't allow them to end. We also don't allow them to change from type I to type J. You know, that kind of branching is never allowed. And so you might say if you don't want to allow it on any length scale. This should be 0. Okay? You can call this the no tadpole rule or something. Sometimes we call it that. Sort of similar flavor. Yeah.
Do you think of EI as a square root of some Boltzmann factor?
Square root of what?
Boltzmann factor?
Boltzmann factor? I don't think in general there's a statistical. I mean, in general, these wave functions can have be negative and so on. They can have negative numbers in them. So I'm not sure they can be thought about directly in terms of statistical mechanical model. But there are connections with statistical mechanical models. Often they involve absolute value of phi squared, but maybe not always. Yeah. When I and j are equal, so we're going to compute that. Yeah, that's not that's going to be computable using rule 4. Yeah. Yeah. Yeah, that turns out to also be true, but it follows from 3 plus 4, yeah, basically, because you can reduce it. You can reduce whatever that complicated object is to a bubble. Yeah, you're right. It's true more generally, but we don't specify that at the outset. So the last rule is actually the most important one in terms of computing things. The last rule says if I have anywhere I have a picture that looks like this H, these lines coming in, I can replace it by a picture that looks like this I. You can see that so there's some, this stuff is going somewhere. So I can make that kind of replacement. Okay, but to do that, I make the replacement, but I have to multiply by this F symbol, which is a function of the 4 external legs. That's IJKL, and then the 2 internal guys, M and N. It's M and N. So the rule says I can go from here to here. If you like, you can think of it as take this picture and then smush it together. So it looks like this. And then in general, it gives you a sum over different ends with some numbers out front. Okay? And so the idea is that once you specify this F and this D, it's going to uniquely specify our wave function. Okay? And I'm going to explain how that, I'm going to give you an example of how that works. So you'll see concretely. But the idea is that there's going to be a unique solution to these equations. And so in that way, we can write down a really complicated wave function by just specifying some simple parameters. OK, so one comment I should mention, which will become it's just something to keep in mind. At the moment, it seems kind of irrelevant, but it'll be important when we write down the Hamiltonian. I'm going to use a convention. This F, you can imagine the case where IJM isn't an allowed branching at all, right? IJM is not allowed. In that case, F is kind of irrelevant because that picture isn't even allowed in our low energy Hilbert space. So I'm just, by convention, I'm going to define F to be 0 if any of these 4 points here have some unallowed branching. So it's just a convention if you like, but I'm going to use that convention when I write down the Hamiltonian. So we define F IJM KLN to be 0 if the branching rules are not obeyed on either side. As I said, it's kind of irrelevant at this point because we're only considering things that obey branching rules. So it's kind of, you would never even worry about the case where the branching rules aren't obeyed. But it will be relevant when we talk about the Hamiltonian because there our full Hilbert space will include configurations that don't obey the branching. They'll be higher energy, but they'll be there. OK, so that's just a note to keep in mind. Yeah. Say what? D and F? No, well, at the moment, they're independent data. I'll discuss in the moment that there are some constraints on this data, actually highly non-trivial constraints, to be able to find a solution to these equations. But for the moment, they're just some data that we're going to try to write down a wave function. Maybe we'll fail. I mean, I'll get to that. So you're a little bit ahead. Are there other questions? OK. So maybe, great. So 2 more things. Yeah. So I have to mention one more comment. I'm going to make one more comment, and then I don't know if I'm going to have time. But hopefully, I'll give you an example where we compute an amplitude. If not today, then we'll do it tomorrow. But before I go ahead and compute an amplitude, I need to explain some notation that I'm using in these equations implicitly. And this has to do with the trivial string that people were asking about. So actually, although up until now I've only had my index run from 1 into n, 1 or 2 or 1, 2, and 3, now in these equations, my index is going to run from 0 to n. OK, so I'm introducing a new type 0 string, which I'm calling the vacuum string. You can think of it as, in terms of the spin language, it's like, well, it's a spin in state 0, and usually we don't even draw a string. But you can think of it as you can either say there's no string there, or you could say there's a type 0 string there. OK? But in these equations, these indices can go from 0 to n, not just 1 to n. Okay? And what's nice about that is that then each one of these equations actually summarizes a whole collection of equations, because in the old notation. So let me give you an example. This equation here, equation 3, it actually corresponds to 3 separate equations in the old notation. Because some of those strings could be type 0 strings, which if we were drawing it in the old notation, we just would draw nothing there at all. So let me just show you how that works. So as I said, it's kind of a shorthand for summarizing equations, this notation here. So as an example, let's look at this third equation, which was this no tadpole rule, I, J, K, L. So the way in this notation, I say this equals 0 if I is different from J. But if you were to write it in the old notation, what does this actually translate to in the old notation? Well, I and J can both be, I could be 0, J could be 0, in which case this equation actually looks like this in the old notation. So this is like a special case, if you like, of this equation, which is the case where J equals 0, it tells you this. If you see a picture like this, you get 0. But there's sorry?
Now by the new notation, you're also specifying the branching rule, which allows 0 L.
Exactly. And 0, 0, 0. Yeah, as a special case. Yeah. So this is one special case of this. Another one is, of course, J could be 0, in which case it tells you that this is, maybe this is a little pedantic, but this is 0 if, whoops, I drew the same one twice. Sorry, this should be a J. I could be 0 in that equation, in which case it tells you this diagram is 0. Of course, it looks exactly the same, but just to explain to you what this notation means. So and of course, then there's the third case. So this is the case where J is 0. And this is the case where I is 0. And then, of course, there's the case where, say, neither is 0, in which case it would just, it would just be the same as our old notation. So all I'm saying is that one equation up there actually defines 3 equations if you don't include the vacuum. If you want to write, not include the vacuum string, I don't know if that's clear. Yeah. The second constraint. No, that one's just for a loop by itself. Yeah. Okay, so anyway, this is maybe not so important. It's a technical point that the vacuum string is one of the allowed labels. Okay, maybe I overemphasized that. Okay, I think if I how much time do I have? Can I take like two or 3 minutes? I just want to do one example of computing amplitude, and then I'll stop, because I think it'll really help. It'll really help to understand what these things mean, to see an example. Okay, so let me just do one example. I think I'm going to I want to leave those rules up. So let me give you an example of computing an amplitude. Suppose you wanted to compute the amplitude for some picture that looks like this. IJK. Okay, so my claim is this picture, like any other picture, we can compute the amplitude using these rules. Okay, so how would you do it? Well, the first thing you would do is we would use this rule, rule number 4. This is really the useful one. And we're going to use it, we draw a little box like this. See, you can see it kind of looks like that picture over there. You've got 2 strings coming in, 2 strings coming in, and a horizontal one there. So if we apply that rule 4, it relates it to a sum of configurations that look like this. So we reconnect this H so that it forms an I. So it looks like this. I've just replaced this picture here with this picture here. And let me put in the labels. This is still label I, and this is still label K. And now this guy's a new guy, which is I'll call L. And now this should be a sum, according to that rule, sum over all possible L's of F I K J K I L. Okay, so that's using rule number 4. Okay, but now, so we just made that little surgery, if you like, where we replaced this picture with this picture in the center of that box. Okay, but now we can use rule number 3, right? Because rule number 3 says it's this no tadpole rule. If an I comes in and a j comes out, it's 0 unless I equals j. Well, here we can see an L is coming in and nothing is coming out. That's why I emphasized here this vacuum string is a special case. So that rule tells us if an L comes in and nothing comes out, you also get 0 unless L is 0 itself. So there's only one term that's non-zero in this sum, which is the one where L equals 0. So L equals 0. So I put a 0 here, and then the 0 string I don't even draw at all, so it looks like this. Okay? That's the only non-zero term according to rule 3. And now finally, we can use rule 2. Rule 2 tells us each one of these loops is worth a factor of di. So if I get rid of both of them, I get Fikj ki0 times di times dk times phi. If I delete both of them, it's just phi of the vacuum. There's nothing left. Okay? So, and now by convention, it's just a normalization convention, we'll define the wave function evaluate on the vacuum state to just be 1. Okay? So then altogether, we've computed the amplitude. It's Fikj ki0 times di dk. Okay? And that's an example of one amplitude that we computed using these rules, but you can do it for any amplitude. You can convince yourself there's a systematic way of doing it, actually. Any term you want, you can do it, although the calculations get more and more complicated, in fact, exponentially complicated as the diagrams get bigger. But in this way, we've specified a wave function just by these simple parameters. Okay. And next time, I'll talk about whether there's any solution to these equations. We sort of skirted that. What I've tried to tell you now is there's at most one solution, because you can uniquely calculate the wave function. But actually, most cases, there are no solutions. We'll talk about that next time. But that's a very important point. Maybe I'll stop there. Yeah. Yeah. So then.
Would that be consistent?
Yeah. So this is going to be related to what I'm going to say, which is that there's some consistency requirements on F and on D for these rules to be correct, right? So I think you're saying I could kind of rotate things, and then I get another equation that looks very similar, but F is on the wrong side. Yeah. So there's some kind of consistency requirement on F for those two equations to be consistent. Yeah. So they will come to that, but only very special values of F and D actually have a solution.
It seems that these 4 rules are all the information. So how to use these 4 rules to actually construct this component?
Well, that's what I'll talk about. But it turns out the Hamiltonians, it's basically, these are parameters that define the Hamiltonian.
But instead of construct the ground state,
Yeah, you could do that. But then I write down that Hamiltonian, and it wouldn't be that illuminating. You would just look at the Hamiltonian, you'd say, where does that come from? What does that mean? So that's why I'm taking this route. But ultimately, the Hamiltonian's a Hamiltonian. You could just analyze it directly. You don't have to know any of this. But this gives you some picture.